Hi there, welcome to the second video for Chapter 6. In the first video for Chapter 6, we explored voltage. Now that we know that voltage leads to charge flow from high voltage to low voltage, we can now take a look at something that you're pretty familiar with already and figure out how it applies to all this theory we've been learning. A 9-volt battery, or really, in general, any battery. It could be a 12-volt car battery or a 1.5 volt AA battery. Those, same idea, right? So you have a little AA battery here. You've got one terminal of your battery that is going to be at 0 volts, and the other one is going to be at whatever the voltage is of that particular battery. So for this one, we have, I believe this is the negative terminal of the battery, so that would be at 0 volts, and then this one would be at 9 volts. So this means that if we connect metal to the two terminals of our batteries, then we can supply different voltages across that metal. And if we do that, then we will cause charge flow to flow from the positive to the we call it a negative terminal of a battery because it's less than the positive, but usually we refer to the negative terminal of the battery as 0 volts, and then whatever the positive terminal is, that one is the one that has all the positive charge that's ready to flow downhill. Now, obviously in this battery, the charge cannot flow downhill because it doesn't have any way to get there. The whole idea behind a circuit is to allow a path. Now, it doesn't do us much good to just put a piece of metal across this thing, because then all we're doing is just wasting all of this stacked up charge that we have and not doing anything with it except letting it flow downhill. It's much more beneficial to us to put a device across this thing. Let's choose a circuit. So sometimes what we do, we'll apply like a battery here, and I don't want to get into circuit schematics, but you can, if you learn circuit schematics, you can do this very easily. You don't have to draw so many pictures. But what I can do is I can take a positive terminal of my battery and my negative terminal, and I will have some voltage here. Let's say this is 9 volts and 0 volts. And then what I can do is I can put a bulb on the different terminals of my battery. What that means is that my bulb is going to have like a little node on one side and a little node on the other. And this allows the charge to flow from the positive terminal of the battery through the wire into the bulb, through the filament of the bulb, and out the other side of the bulb and toward that negative terminal of the battery. This is basically charge flowing downhill, but it does it by going through the bulb. So this is a circuit. Now that we have a circuit, we can explore the motion of charge. Now the battery is going to work its hardest to make sure that this stays at 9 volts. Now other things, like when you shock yourself on a doorknob, or you see sparks flying across blankets and things like that. What that is some charge that's built up, and then when it flows from a place of high potential to a place of low potential, well, the story's over. It's done. But a battery is really good at making sure that if charge flows out of the positive terminal and toward the negative terminal, that another positive charge is waiting there to be delivered if it's needed. That's what batteries are good for. They're basically there to make sure that a potential is available. So we can always count on there being, if we have a battery here, 9 volts of potential difference between the positive and the negative, at least until our battery runs out. So what is this charge flow? Well, we can define that. That is given by another one of our terms, current. The current and conventional current is the flow of positive charge. Current is given as the amount of charge that flows in a unit time. Now we usually write that as I, the current is I, and that's going to be equal to the amount of charge that flows in a unit time, right? I do not know why they use I for current, but they do. So now you can calculate, if you know how much charge manages to go by your bulb or through your bulb in a certain amount of time, let's say a minute, then we can figure out then what the current is. Now what's the unit of current? The unit of current is the ampere or the amp, and is given by a capital A. Okay, so what is a capital A or an amp equal to? It is equal to 1 coulomb of charge every second. Now this is cool because what this does is it says, hey, I can look on these batteries and see maybe if I know how much current is flowing, right? You can't see that on the side of the battery necessarily, but sometimes you can. But if you measure the current flow here, then what we'll do is we'll say this has 100 milliamps of current. Well, 100 milliamps, that's silly. Why don't we put that in amps? That equals, we know a milli is equal to, like a millimeter is equal to 1,000th. So 1,000th of an amp is 1 milliamp. So we would need to move our decimal over by 3. And if you do your unit conversion, then you will find that to be 0.1 amps of current. Okay, so we have 0.1 amps of current. Let's write that down. I equals 0.1 amps of current. We might ask the question, how much charge moves through the bulb in an hour? Okay, now that we have that, we can, let's scoot down so we can actually do our calculation. So this problem that we have set up is how much charge moves through the bulb in 1 hour. Well, it's important for us to be able to first calculate the number of seconds. Why? Because remember that an amp is equal to a coulomb per second. Well, if we have the current is equal to the charge that moves through the bulb divided by the time that it takes for it to move through the bulb, then we need to convert this for coulombs per second. We need coulombs per, and time needs to be in seconds. So not 1 hour, but we would instead write that time is equal to, remember how many seconds are in an hour? 60 seconds in a minute and 60 minutes in an hour. So if you did your conversion, you would get that the time is equal to 3,600 seconds. Now, if we want to solve that charge, then in order to get rid of this pesky t, we're going to need to multiply both sides of our equation times t, which means that we would get our current times the time, and that is going to equal 0.10 amps. Now I'm going to go ahead and write our amps as coulombs per second because we're about to multiply this by 3,600 seconds, and that way we can cancel our seconds, units of seconds. You can write amps there, and that's totally fine because this is equal to the same thing. But what I wanted you to see is that we're going to end up with coulombs as a unit. This gives us that 360 coulombs have flowed through within that hour of time. Okay, so this gives you a sort of a sense of what current is. So we want another feature to our circuit. We see that current is equal to the amount of charge that flows through in a certain amount of time, but where did it come from? So we have 0.1 amps that we had in our previous example there. Why though? Why 0.1 amps? Well, that's determined by the bulb. If you put one device in your circuit, then it's going to allow current to flow at some rate. And if you put a different device in your circuit, it'll allow current to flow at a different rate. So what we're interested in now is something called resistance. And resistance is it's the resistance to charge flow, right? So it's very easy for us to compare the voltage that is supplied to a circuit with the current that manages to make it through the circuit by analyzing the resistance. So the resistance then is simply equal to the voltage or electric potential divided by the current. What this means is that if we have a resistor like a bulb, right? A bulb has a certain resistance to it, and if you want to increase the current, then you'd have to increase the voltage also. So we can rearrange this equation so that we have that the voltage is equal to the current times the resistance, and we can also rearrange this equation so that the current is equal to the voltage divided by the resistance, right? So any of these works to explain the behavior of our circuit. We can now calculate what the resistance is on our bulb if we know that the current is equal to 0.1 amps and we know that the voltage is equal to 9 volts, right? So the resistance then would, by this relationship, the resistance would be equal to 9 volts divided by 0.1 amps. If you run that through your calculator, you'll get a value of 90. Now, what is the unit for this? Well, it's not volts per amps, because although it is equal to a volt per amp, that's not the name that we like to give it. We like to give it the unit of ohms. I know that's a weird word, but that's actually someone's last name is ohms, and as a matter of fact, this law is Ohm's Law. So, what unit? Well, ohms. How do we write that? We actually write that, this is almost dad joke level, as a Greek omega. It's terrible, isn't it? It's awful. Alright, so this is how we write ohms, is we use this little omega, Greek omega. Okay. So now we understand some very important features of circuits. We understand Ohm's law tells us that we know that the voltage is the sort of energy that's applied to, it's not the energy, but it's related to the energy that is supplied to our circuit that allows the circuit to push charges through. We know that the current is the amount of charges that are flowing through in a unit time, and we know the resistance is what controls that current. Okay, so these three are the meat of this video, and hopefully you can rearrange that however you need to. On the next video, we'll talk more about circuits.